In the last couple of weeks, I've talked about how probability theory in general, and Bayes' rule in particular, can be used to represent uncertainty in presenting and interpreting evidence. This has mainly been in the context of expert systems, although that phrase hasn't passed my lips for a while. There are two basic problems associating with using nothing but probability to represent uncertainty. And if you took even a cursory glance at the video I produced that gave a demonstration of Bayes' rule in a JavaScript program, link below, you'll certainly be familiar with one of them. The advantage that the proponents of probability theory laud over anyone who suggests using any other approach to handling uncertainty is the fact that probability theory is the only uncertainty calculus that is mathematically rigorous. The other approaches always fudge the mathematics in some subtle way, and any attempt to overcome those fudges simply takes those approaches closer and closer to probability theory. However, just because an approach is mathematically sound doesn't necessarily make it either useful or practical. To use Bayes' rule, we need data, masses of data, in the form of conditional probabilities. Indeed, as the Bayesian network becomes more complicated, the amount of data needed explodes exponentially. If conditions A and B lead to condition M, conditions C and D lead to condition N, and conditions M and N in turn lead to condition X, then the probability of X will depend on combinations of no fewer than 6 different conditions. M and N directly, of course, but also the probability of M given A, M given B, N given C, and so on. The more steps that are added to the logic, the more convoluted these conditional probabilities become. One way that expert systems based on probabilities has of ducking that problem is to assume that probabilities are independent of factors earlier on in the line. In the example we have on the screen, we could assume that X depends on M and N only, and slice off any dependency on A to D. Well, pruning each probability to 1 or maybe 2 steps back in the chain would certainly cut down the amount of data required, but it also leads to small errors that can mount up further along the chain. Moreover, it means that the system can no longer claim to be mathematically rigorous. I'm not saying that any probabilistic system must be mathematically flawed, only that the much flaunted rigour is no longer guaranteed, in which case you might as well use a simpler but more practical system. Indeed, the AI pioneer Edward Feigenbaum, who led the team that developed the blood disease diagnosis program Mycin, once joked about the reason he didn't use probability theory to handle uncertainty, but was forced to develop his own calculus. It's hard enough, he said, to get probabilities for individual symptoms out of my medical colleagues. When I mention combinations of symptoms, they stop talking to me. However, there is a more fundamental problem with probability theory, and that's how you're supposed to represent ignorance. Let's take the example of a die, for instance. Yes, I know you're tempted to call that thing on the screen a dice, but that's the plural. One of them is technically known as a die. If you toss a die, what's the probability that it will land on a 6? Well, if it's a fair die, the obvious answer is 1/6, or 16 2/3%, same as for any other of the 6 values. But what if we don't know whether it's a fair die or not? I hand you a die about which you know nothing, and ask you what the probability is of it landing on 6. That die could be a fair one, or weighted so that it lands on 6 every single time. You can't give me a numeric answer, and yet I press you for one. After all, if we're going to get some computer program working on this, it needs a number, not just a vague I don't know. All we have to go on is the assumption that the die is fair, and that the figure we want is 1/6. So using probability theory, there is no way of differentiating between a die that we know is fair and one about which we know nothing. Of course, probability theory has its die-hard supporters. I've listed some of them on screen. They claim that probability is perfectly capable of handling all uncertainty issues. You'll notice that all the papers mentioned are very old ones. That's because this East Side-West Side war is quite old. Since the advent of neural networks, the focus of attention has been well and truly taken off expert systems and symbolic AI as a whole, so differences in opinion such as this one have been reduced to one huge nothing burger, as they say. However, there were at the time those who claimed that the most important criterion of an uncertainty calculus is that it's useful. It doesn't have to be mathematically perfect, especially if that perfection comes at the price of inconvenience, but it should be practical and relatively easy to implement. After all, the human reasoning which the expert systems are trying to capture are hardly rigorous themselves. There was one researcher, for the life of me I can't remember who it was, and I haven't been able to find a reference to it on the internet, who reported that trying to extract data from human experts was mathematically hopeless and merely reflected hunches and instinct. For instance, he asked a medical doctor what the probability was of a patient having a particular symptom if he suffered from a known disease, and the doctor replied, about 70%. When the researcher then replied with, so the probability of the patient with that disease doesn't have the symptom must be about 30% then. The doctor immediately retorted, oh no, I wouldn't say that, about 10% maybe. As a fight back against the pushers of probability theory as the only acceptable calculus, the advocates of a more flexible approach came up with a checklist of 7 qualities that any uncertainty calculus should have in order to prove sufficiently useful and reliable. Horvitz, Heckerman and Langlotz in their 1986 paper listed these qualities, and I summarise them here. Firstly, any proposition, any statement which might or might not be true, should be well defined. This is common sense. Indeed, all 7 of these are really common sense. It doesn't mean that the proposition should be exact. The statement that John is tall is well defined, although the word tall means different things to different people. Of course, the statement doesn't have to be true. If the belief level in that well-defined statement turns out to be 0, then John isn't tall. The scalar continuity property states that the belief in the statement can be expressed as a single number. Up to now, we've expressed a belief in a proposition as a probability in the range 0 to 1, but there are some calculi that express it in the range -1 to +1, with -1 representing impossible, +1 representing certainty, and 0 representing complete ignorance. Any range would do, as long as you can make the maths work. We would usually expect a number to increase as a belief in the proposition increases, i.e. a proposition with a belief of, say, 47 on some scale will be more likely than one with a belief of 23. This doesn't mean that we can't consider ranges of values at any point. Dempster-Shafer calculus, for instance, talks about the support for a proposition and the plausibility for the proposition as the lower and upper limits for the belief in that proposition, i.e. the belief is still a single number. All we can say is that it's somewhere between this value and that one. The completeness quality is the flip side of the scalar continuity property. That is, no statement can be considered by the calculus unless a belief value can be assigned to it. If you can't put a number to it, we can't use it. Okay, so far our calculus works on nothing but well-defined propositions, each of which must have a single belief value, or a range of values in which that belief value must lie, assigned to it. What else? The context dependency property states that the belief in a proposition can depend on the beliefs of other propositions. Well, that's an absolute must if we're going to use these things in an expert system. After all, the whole idea is to take first-hand evidence and to use some sort of formula to turn it into conclusions, maybe with intermediate conclusions between the two. It also follows that we need a formula or some algorithm for turning the beliefs in the evidence to the beliefs in the conclusions, and the necessity for such a formula is the hypothetical conditioning property. Just as we can have a certain belief in the truth of a proposition, we can also have a belief that it is false. As the belief value in the proposition increases, then the belief that it's false must decrease, and vice versa. This is the complementary property. Essentially, this means that the belief that X is true and the belief that X is false must meet in the middle somewhere. You might ask how we might deal with that vague response from the doctor, who is 70% certain that a patient with certain disease would show a particular symptom, but only 10% certain that he wouldn't. Well, that's where we resort to the idea of ranges, in which the belief value was known to lie. In that case, the lower limit for the patient having the symptom will be 70%, and the upper limit will be 90%, with the remaining 10% indicating the doctor's belief that the symptom wouldn't be there. The actual belief will be a single value somewhere in that range, and presumably its negation will be 1 minus that value, or 100% minus that value. Finally, the consistency property says that two propositions that are considered equally true must be represented by an equal belief value. All propositions that are known to be true, for instance, should be represented by the same number indicating certainty, such as 100%. All propositions that are known to be impossible should also be represented by the same value, presumably 0% or similar. The same can be said for all propositions that are true to the same degree between these extremes. To meet the consistency property, the belief of any final conclusion should be independent of the sequence of steps taken in getting there. If a final conclusion is that the patient is suffering from the disease lupus, for instance, then we can't say that the belief in this diagnosis is 70% if we take one particular route through the evidence, but only 50% if we take another. Any discrepancies that arise, and there will be some because it's in the nature of the beast, must be resolved somewhere in the system before the process finishes. These 7 qualities are seen by several researchers, or at least they were in the late 80s and 90s, as a rebuttal to those who said that probability was the only representation that was sufficient for representing uncertainty. Provided that an uncertainty calculus could tick every one of these 7 boxes, then they would consider it overcoming any objection to its use in calculus. The idea was that this checklist would become more and more widely accepted until the probability-only people would be sidelined. It would have been interesting to learn which side would have won had this disagreement been carried to its conclusion, but by the late 1980s, neural networks and connectionist architectures were increasing in popularity, and since then they have almost completely eclipsed symbolic AI and the arguments that led to it. This conflict is simply no longer an issue. So there you are. I did say that I would make a start on some of those non-probabilistic calculi this week, and had hoped to do so. But I must have talked for well over 10 minutes so far, and I can't really do justice to any of them without making this video prohibitively long. Sorry about that, my apologies. All I can do is to state that I will start the next lecture with Dempster-Shafer calculus, and that's a promise.